There's Brendan.
Hello.
Hi there.
Hi.
Managed to make it.
Well,
Hi there.
if none of us are able to do that, we have to find.
Sorry, Paul.
It's a question of time. I think the people here have the capabilities. I think it's just putting the time in. I'd certainly, I haven't gone through the code versus the equations line by line at this point, but that's something that would need to be done to identify which equations line up with which parts of the code. And then, since we understand the equations basically, and then there's, some form of solving the equations in the code, we just have to do a lineup and then find where we can introduce those elements. So I'd be fine going through the code with other people who probably understand the equations a little bit better, but this is just a time thing, putting the time into it, along with all the other projects that I'm working on, at least.
Maybe Brendan can do this, who wrote the paper.
Well,
I can go over the code with anybody if people need some insight into the code, just from a general code perspective, since I do a lot of coding.
Then describe then what the renormalization would do to the addition of this rotational diffusion term. Will it do something special, or is any kind of approximation being done?
Who are you speaking to, David? Are you speaking to Justin?
are you asking me or?
Yeah, maybe Brendan came in a bit late. Maybe you can tell if you can add the rotational diffusion term to the renormalized version of the equations, because they are the ones in use in the simulation software.
So there are two problems that were suggested, two modifications to the program that exist that were suggested. One was, putting, forces at two different points to get a spin going. Another one was to have that angle of the reactions, so that some of the particles, when they're diffusing, that they're diffusing at an angle. That's sort of one of the equations that you put in the paper. I believe it was equation 6.
I guess there will be some cross terms.
Right, so that when we do the diffusion in the code, just where in the code is the diffusion stated, and then make this modification to add direction to it.
Will the end result be some rotating particle?
Well, one of the things I was thinking, David, was that if we look at Paul's diffusion equations, that rate of change of geons with respect to time has terms added to it. Each of those terms that are added have the same dimensions, because when you add in physical equations, one term you add, the next term you add must have the same dimension. So I was thinking of it a bit like a velocity vector, except with not just three, but like more like five vectors going round. So a normal velocity vector, you might think of like velocity going that way, and velocity. So I was just adding another term, and that term, I was just playing around with it, but that term that added would be the rotation. So that would, so it's not velocity, it's concentration or potential per unit time. So there's this, it's a kind of velocities in there. It's a kind of velocity. It's concentration per unit time. So just add the, I think it's the fourth or fifth term would be the rotation. So when you're adding vectors, when you're adding in the physical equations, the first term, say, is concentration per unit time. The next term, when you add it, is also concentration per unit time. Or if you're doing velocity, one term will be velocity. If you add the next term, that must also be velocity.
All right. In the code, I see there's this V. I don't know if that's the velocity that we're talking about.
Yeah, let me just get it up.
A V array. In the Model G C code.
Okay. So if I share this screen, let me just try and get back.
Yeah, share the screen again so we can see it.
I'm just trying to. Okay, so go to share. And what's this now? Share. Okay. Can you see that?
Yes.
Let me just see if I can make it bigger. See. Control. Make it bigger. So this equation here. This is for geons, gravitational potential. So concentration in terms of potential per unit time. This term here would also be concentration per unit time. So with this one and this one here and this one here. So that's what it looked like before. So it's just this term wasn't there before. So that's also concentration per unit time. But it's got an angle of that velocity is changing with respect to direction. It may be remaining the same velocity, but it's changing direction. So being a vector, it's different at each point in the circular motion. And then this term here, del of the concentration, would make all of this here concentration per unit time. That's my idea behind it. So it's just a bit of guesswork, a bit of understanding, and a bit of guesswork, but something along these lines. So this is like a sort of 1, 2, 3, 4, 5 vectors in a kind of region. But it may not be that, but that's my kind of initial guess, which is giving me some confidence in trying to work with it.
So G is the geon concentration.
Geon is the concentration is, say, moles per unit volume, moles per meters cubed. And these. I mean, if you want to give it, you just put it per meters cubed or moles. Moles being the amount of substance, the amount of geons, the amount of etherons per unit volume. In terms, you could maybe make an analogy with moles being the amount of substance.
So is this one of the reaction equations?
Sorry, Justin?
Is this one
Yeah,
of the reaction
one of the
equations?
Model G equations. So we obviously solve this equation here. We solve for G. So we solve this. We bring this time element up here, make a partial differential solution, and we get G out of it. We get the concentration or the potential out of it. And then what I was thinking was those one-dimensional plots that you saw with, on the x-axis it had displacement, on the y-axis it had concentration. I was thinking maybe if it's 1, 2, and 3 dimensions, maybe that's a slice through either 1 dimension, 2 dimension, or 3 dimensions. So the y-axis represents 1, 2, or 3 dimensions, depending on whether it's slicing through. That's what I'm coming up with at the moment.
Okay. And is this line 39, is it changed if you normalize, or is it the same?
I mean, it will have the same dimension. So it would have the same. Each of these two terms will have the same dimensions. Because when you add in physics equations, when you add, they all have to have the same dimensions to keep this the same dimension as this. So this will have the same dimensions as just before. So Paul Laviolette took this out when he did the original derivation. Paul had this as the convective term, not with the omega. It was just velocity, standard velocity. He had this term taken out because if you look up here, where is it? So this term, where is it? Convective flux vector must also be taken into account. Okay, let's go back a bit.
I don't think I took it out. I just didn't include it in.
Because this term accounts for the radial diffusion, whereas this term is the convective flux vector, which is not necessary if you're just. So we just included this one, which accounts for radial diffusion, is what I'm understanding, and this one here was just neglected, as you can see.
All right.
What do you mean radial diffusion?
Well, I was thinking this is translational.
Yes.
So I'm putting this as the velocity omega for rotational velocity. Whereas you've said, I'm just saying, must also be taking account of velocity.
Okay, this thing could be good to read. I will go through it if I'm.
Okay, let me see if I'll put it here. That should be.
But it looks very much to like a convective derivative, that thing.
Okay.
Which term are you talking about?
The last one.
So can you see here? Can you see here now? Look, however, for many of the situations we'll be considering, we may assume V, the convective term, equal to 0, and neglect the second term. So if we neglect this term, which is model G.
Okay, V was assumed to be 0, yeah.
Okay, because that's convective term. So we've neglected that. So we're left with this, and this is like the translational diffusion. Whereas this one here is neglected because we don't need it. We're just working with translational diffusion. And if we make this a velocity, a rotational velocity, omega, the V component of omega, then this is.
Yeah, this is just a pointwise description V. It can be rotational or not. So if we just add it, we will get both cases included.
Yeah. So then you go down here. So I've gone through this is rotation and vortices of fluid dynamics. So down here, so now we look at, this is vortices. Vortices are between 2 omega. I think you treat that as just omega is that, and then omega for rotational is that.
Yeah.
Okay, and then if we go down.
Has anybody looked at the work they've done on quarks rotating to make spin?
I just put it in I put it at the bottom. I made I had a quick look at it, but I made a reference to it here. So I'm not saying what I'm saying is completely accurate. I'm saying that it's a bit of guesswork, but I'm sort of getting some confidence out of it. Here, simulating. So that's the simulating quarks reference.
Okay.
That's the presentation.
Oh yeah.
So you think we can, any of those papers can help us, or maybe the people who wrote them?
Yeah, in this one here, the guy who wrote this, he stated vortical motion as being like That's where we're going now with this. But see, let's go up. He's saying he's treating vortical motion. So this is the vortices here. He's just saying omega equals this. So he's defined it as this. That's the 2 omega. He just called that omega. He's taken out the 2. He's just treated omega equals this.
Yes.
So he's just.
So you think there should be some initial conditions on V in the volume?
Let me just get that paper up and have a quick look at it.
If
Okay, so it's not. My Wi-Fi, I had to turn the laptop on and off a couple of times to get the Wi-Fi working. So it sometimes plays around a bit. So this is not going down here. It's not. Let me just refresh that. Okay, here it is. Here's one of them. It's a definition vortex vector. This is where I placed it on. I placed it on the question on Mathematica,
yes,
and I didn't phrase the question very well at first, and I went and rephrased it. He gave me a -1 for
yeah, that's what I do.
And then I put the answer. He wanted me. I was saying, I think it's this. Can someone help? And he wanted me to put an exact answer. He then took off his comment later.
Is that where you got it from? This reply?
Sorry.
No, okay, you wrote it yourself. I see.
I just wrote out the reply there. No one's voted on that. They just left it.
Yeah.
I'm not sure about it.
What do you mean they gave you -1?
When I first wrote it, it was in a way that he wanted more information, and he just put -1 there. So it's. I mean, if they can give me the answer, put -1. I don't mind. If they show me what they think it is, but they just left it there like that. And where is it?
So do you think that's helpful, what they said?
He took off his comment. He just said, you should give more information. I put a link to the previous question I put up there, hypothetical subparticle.
Maybe we should go in there and vote up the question on.
This one here, they like this one. The first one I did 8 months ago. He voted 2, and someone's put a favorite question.
Uh-huh.
So I made a link to that. I also tried to give an answer, but a few people may have liked that first straight away. So if we go down to,
maybe we can contact the authors of the papers, the court papers, to see if they have some ideas. Does somebody want to do that?
I'm happy to do that.
Okay.
Let's just I'm trying to find it here. Here it is here. So
and maybe they might get interested to be part of the group. Who knows? So since essentially we're doing the same thing they are, just a different type of particle or ether on.
And also, if you look at this one here, this is the presentation. So something like so vorticity-driven effects in rotating quark-gluon plasma, and you can see down here he's defined omega vorticity. That's half. Okay, so he's calling it half. But he's calling it vorticity. So sometimes they just define things in different ways. But here he's defining vorticity as the same as the other guy defined rotation. So it seems rotation and vorticity are very similar.
Uh-huh. So what did they assume regarding how could they say they had vorticity in their environment?
Well, I assume this is like this is the definition of the
Yes.
rotation of a single of one particle. So it's the rotation. So it's one element in the simulation, as far as I can see. These are I work in when I'm working particle physics. These are like energy and momentum.
Uh-huh.
They have quite a strange way of dealing with units. They try and make all the units of mass, energy, and momentum just in terms of energy, GeV or giga electron volts and things like that. So they change the units so they can manipulate the equations more easily. They just make mass, energy, and momentum the same.
Yeah, that's momentum is like velocity versus multiplied by mass, but the energy is like mass multiplied by v square.
I know, but they kind of like they alter the units and then they change them. They play around with the maths a bit, alter the units to make them all the same kind of units. And then when they want to solve the equation later, they change them back into their units of momentum.
All right, so they calculate in a square like this.
They do. Yeah. So these would be like particles, and they would have a momentum.
Yeah.
I was thinking.
Okay, one way our situation differs is that we have radial flow in addition to vorticity. The vorticity is caused by the radial flow, the inward and outward flow, becoming somehow unstable and causing the flow to turn. So that's different from what they're doing. They're not assuming a radial flow. Our situation is trying to simulate like water going down the drain in a bathtub.
Well, I was looking, Paul, at your term here, this one here. You were talking about the angular velocity being omega 0, and I was thinking of the rotational convective term being v omega. So that's the velocity. So the velocity could be. So if we could put in a value of omega, we can get the velocity. We can get the velocity out of it. So we could just give the xy rotational etherons. Just give them a value of omega. Say find the value of spin that they're using for a particle and give it that value, and then you can get out the value of v omega. So that could be the same magnitude but different. But because it's the same magnitude, but it's changing because it's changing direction. So it's changing direction.
Okay.
Yeah. So I mean the velocity vector we already have. The equations are predicting this radial flow in and out of the particle. So the question is somehow that flow turns into a rotation. Yeah.
Yeah, it's not easy. I see some of this, but the full picture I don't get. But maybe I see enough to make a simulation. But
playing around, it's just what I did with my PhD work was just playing around. So you just try something, suck it.
Yes,
suck
I
up V. Just
I
try
think the velocity field should just be added, and then we see what the results are.
So we could give it a value of omega. So if we know this, say we know the spin of a subatomic particle.
Yeah, if
So
we
that's
add the velocity field, we can give it an initial value, if you want.
and then kind of like and then so we can know if we give it a value omega, then by
Yeah.
solving this equation we can get out V, and from the V we can put that in the simulation and see what happens with the diffusion.
Yeah, we can just if we assign omega, and we like want to back solve it, integrate it back to V, then we need like we can have like a big rotating fluid, solid body rotation. So we just need to determine then what the center, the axis is of this rotation.
That's what
Should the axis be in the
Well,
middle
center
of the
would be
particle, like AB
Yeah.
here?
The central circle, that area is where you would get the vortex would be due to the X going to Y and Y going to X, rotating. Yeah.
Okay. Yeah, we put this in and see where it ends then. Unless there is some problem with
and we can just adapt the mathematical C++ code. Just adapt,
Yes.
It's already written. We can just adapt it, add a term, see what happens, take that convective term, add it, and then see what happens and play around with it. Just see where we can get.
Okay, we have the relation how the velocity affects the concentration, but is anything affecting the velocity then? Is it a back
But when
term
you've got the
on
other terms, you've got the other
velocity?
terms here. Where is it? Let me see. You've got the so here we've got we've got geons, exons. These other terms are determining the diffusion, are determining the types of diffusion of the brusselator. Then this term here, say that this is the y, x, and g. If we just take the geon, we've got the
Can we introduce momentum? Oh, go ahead.
This is like this is the brusselator with radial diffusion, and then we just like try and add a term and see what happens. Try and add this term to be rotation, and then see what the program does.
Now, can we add momentum?
Yes, we could add momentum, because then we'd have to play around with this to sort of like so this is concentration per unit time. So concentration, so moles per unit, because concentration is moles per meters cubed. So it's per meters cubed per unit time. Moles per meters cubed per unit time. So it's a kind of concentration velocity sort of thing. So so in
the case of water going down the drain, isn't it the momentum that causes it to rotate when it goes down the drain, or is it something else? Is it friction, or what do you think? What do they say?
Yeah, well, I mean, in fluid dynamics, they have like viscosity. They deal with viscosity and things like that. Momentum as well. I'll just bring up that one. Let's just bring up this one here. So let me just go to top. Okay. When I first did that, okay, this one here. You see this one here? So this one here was the one that I wrote back in August 2018. So here we've got, I cut out and copy and pasted from Wikipedia and made a reference to Wikipedia. This is Anne Witt talking about Navier-Stokes. So Navier-Stokes is what is used for fluid dynamics and also related to the Brusolator. So here we've got mass, momentum, and energy.
Do you need all three, or couldn't you just use momentum and get it?
Momentum includes mass, so it's momentum mass times velocity, kilograms.
We know the ether has momentum from what Tesla wrote, and the Grebennikov effect.
Yeah, I mean,
There's momentum to the ether.
Wouldn't the Brusolator people who study the Brusolator, would they include a mass in the Brusolator?
No, mass wasn't included as far as I know. And I didn't include in Model G.
That may mean it may mean
mass
redirecting.
was supposed to be something at the quantum level.
Sorry, say again, Paul.
In subquantum kinetics, mass was supposed to appear at the quantum level, but depending on the concentration of the particle, the ether concentration. But now we're thinking maybe we need momentum at least at the subquantum level. That's what I'm wondering. I mean, we have this experimental evidence which indicates that it might be okay to do that for the ether, to ascribe momentum to it. I'd rather not.
Yeah, it could mean
that's the only way to get this.
Trying to redefine the equation to include mass and momentum, or just momentum includes mass anyway in it because it's mass. Mass meters per second, kilogram meters per second squared. Sorry, kilogram meters per second. Well, we could we could just to start off. We could just try something. Just try this out. Just try anything. See what happens. So we've got this here. This is obviously what Model G is at the moment, and it describes the radial diffusion, and then we can just add this term here and see what happens. Then by trial and error, just like see what happens and then try something else. See if that
So Brendan, you're able to do that?
Well, what I've done is
do that.
What I did is I just got round. I've been a bit busy in other places, but I'm working on it a certain amount. I just ran ETD stepper and just produced.
I mean, not to write it. I mean to model.
To model it.
To actually run, to get a simulation.
Yeah. So what I could do is take this term here and try and where Matt Pulver's solved G. He solved G concentration from this equation. What I could do is then try and include this. I may need that's where Mathematica is quite helpful because you can solve equations of Mathematica, but it's kind of partial differential equations. Not a certain amount. See how far I've got books and things from BSc physics where we solved partial differential equations. But he's done it in the code already. He's done it in the C++ code. So it's just a bit of adapting the C++ code and just seeing how he solved it in C++ and putting this in.
So you have Mathematica?
I don't have Mathematica at the moment. Mathematica is quite good for solving. You can write programs in it, and you can also solve equations with it. So you can you could probably, if you knew what, if I know enough,
Okay, I'd suggested sending you my copy. That's one possibility.
just
I
don't
mean,
have,
I have a copy, I don't use it.
I don't have Mac. I don't have a Mac. I just have a Linux and a Windows.
Oh. Well,
Uh,
okay.
But
Does somebody else want to try it? Somebody else have Mathematica? No. Okay, well,
but what I can do, Paul, is because what I
so,
understand. Go on.
so what, we'll use open source or something like that?
Yeah, I mean,
open,
from what I
foam?
understand, in the C++ code that Matt Pulver's used, he solved this. He solved these equations, G, X, and Y. He solved them for G to get the concentration. So he's already solved it within the code. It's just a matter of understanding the code well enough to just add this bit here. Just try and solve it with this bit. It can be done by hand or mathematics. Just go on.
So,
Okay, so if
saying
we
he
get
solved
that
it for-
added in, if we get that added in, where are we going to run this if we get it all set? We need a computer, right?
Yeah, I can run. I can run it on my. I've got it set up on my Linux desktop. I've got ETD stepper, so it's just a question of going inside ETD stepper,
Okay.
and altering the code so that it includes this term instead of just these terms. And obviously,
So let's look at the code
So
first.
do you think you
I don't know 100% for sure, but I'll give it a go. I'll try and see how far I
I
can.
mean, I'm looking at the code, and I'm guessing the location that needs to be modified. It's in the model G equations, I think. And I don't know if it's a 2-particle or 3-particle or the torus code. Do you want to open up the code?
Me? Are you guys speaking to me, Justin?
Yeah, I can open up the code too if I have it open.
Let's just go to
This would be the website. You got a lot of links in there. I have no clue what you would have. Yeah, that's it.
Okay, so David's put it here. ETD stepper. Okay. Where did you put it? So,
I think it's in the link. You just passed it. It's right there.
that's the ETD stepper simulation. The code is down here somewhere.
Is the get? No, you scroll. Yeah, okay, you found the link.
So the main program is
Not the text one. Go into the CPP.
that
Yeah.
one. That's the main program. So
C code. So if you scroll down, I'm not sure how this correlates. I'm not sure what the V's and the C's are. You have to trace back in the code. But if you scroll a little further down, I believe it's you got the G and V there. So I don't know what the RV of G is. That I'm guessing that's the so there you've got the equations for, if you scroll up. There you have some equations for, scroll down a little. So right there you have equations with 2-dimensional, 3-dimensional. You just scroll right past it. Yeah, scroll up a little. So you got 2 particles, 3 particles right there. Torus, you scroll down a little. You got segment, torus. and scroll down, and then you got three other sections. So you got 3 particle. Now, one of the things he did, he's got these parameters, 665, 64. I think those are numbers that he discovered through experimentation. I think those are all the coefficients that he discovered around the equations. So those may need to be put as, from an equation perspective, they actually had, letter names associated with them. So this may be the equations that, my best guess, that need to be modified, but to understand, we need to trace back and see what the variables are, what those constants that we see there. I think those constants are actually the coefficients around the model G equations.
Yeah, those out-commented things are the seed values to get the torus and to get 3 particles and so on. So these are the seed values to get different solutions. So if you want to see the real differential equations, you have to go elsewhere.
Elsewhere in the code. Elsewhere.
Down, further down. Is it here? No.
So I believe the model G are the equations that he put out. I believe the other code is the code that he got from other locations in order to do the simulation.
He's got it. So you're saying that
if you look at the other,
find something else here.
There's only like
EXP
3 or 4
time.
CPP programs.
Which one? Yeah.
No, it'd be the CPP code. H is basically just
Take
definition library. Yeah. So that I think is the part of the simulation code, the Runge-Kutta method. It looks like 4-stage Runge-Kutta. That's a mathematical simulation package. Although he says he's the author, he might have gotten it from someplace and make modifications.
Yeah, this is not easy to read, I would say.
Let's go through this.
It just requires just like piecewise, just stepping through it.
Yes.
It's not required just going on Stack Exchange or some forum to understand the code and just piecing together step by step. Understand? There's plenty of forums and Stack Exchange. If you don't understand something and you can't find something, just ask a question on Stack Exchange. And just if it's a good question, it'll get answered. But if it's not on Stack Overflow, I just go to Superuser, right, or some other one.
So look at the main comment there, just to let you know that Runge-Kutta method. You can look that up, and it'll scroll up. Okay, so it's a 4-stage Runge-Kutta. Okay, so go look that up, and you'll understand what a Runge-Kutta method is. There's an explanation. RUNGEKUTTA. 4-stage Runge-Kutta. Okay, see that at the comment at the end on line 8. Line 8.
That one there.
So
yeah, maybe you should go into that code instead. If it seems like he implies that
you just look at that online, you just kind of what I do is I just like.
Okay, so these are methods used to solve equations.
In the paper he published, he explained why he used that in the paper he wrote.
Okay.
Go into another C++ file that is called exp time diff and check what we have there. On top there, second from the top,
That one.
that one.
Right. So I think both of these are tools, and I think and I may be wrong, but my guess is that both of these are tools used to solve the equations, whereas the other code is the specific set of equations.
Yeah, go down and see if what we get here.
See, FFT, that's fast Fourier transformation.
Yep.
Yes.
So this looks like it's fast Fourier transformation code. So if you can look up fast Fourier transformation, get an understanding of what.
Well, go
that
down a
type
bit
of-
more.
Okay, so those are the two things you may want to look at to understand these other two packed CPP codes. One is a fast Fourier transform, it looks like, and the other one looks like it's a equation solver using the Runge-Kutta method.
That was
Okay.
that was.
And then the other code we're looking at is the actual model G equations that this other code is working around to doing the solving on. That's my guess based upon naming comments.
I could always email Matt. If I'm stuck and ask him a question about it.
Right.
Returns non-zero to non-success.
Yeah, go down more here. This seems to be set up only.
Yeah, I believe that it's a package. He probably had to make some modifications specifically. It's been a long time since I wrote a Runge-Kutta method, so I don't recall. But it's undergraduate level. It's not that complex. Both cases are. Fast Fourier transform is a little.
This one's
a little more complex.
So this is like an equation solve, obviously.
Yeah, I believe both of these are equation solvers, and the Model G is basically the equation code, and those are the three big programs here. So if we were going to be making modifications, my guess is that, particularly just that one, vectors, I think that would be in the other code somewhere around the area, because it looks like there were like 2 or 3 iterations on the code, so the equations might be broken into several different pieces of code, but it needs to be walked through to see where things are. So fast Fourier transform and Runge-Kutta method.
Let me just try this fast Fourier. See what it says on that.
FFT is a giveaway. I mean, whenever I see FFT anywhere, it's fast Fourier transform.
Yeah.
He seems to does a transform to simplify some step, so it will totally be a speed up.
Yeah, and he mentioned fast Fourier transform. So even without that comment, ICFFT, I'm going to say, hey, it all looks like a fast Fourier transform code. That's the name he uses. I'm sure if you look
This
under fast Fourier
W is
transform.
just the name of the library.
Okay.
So take away the W if you want to see. Yeah.
Solving questions equations.
If you search on exponential time difference, you will get what he based his code on.
FFT exponential.
That's why it's called ETD. Yes. And he also called it spectral solver.
So it's basically using fast Fourier transforms to solve differential, integral and differential equations.
Yeah, and I think Winjikuta is part of that. Codes usually, for dealing with round-off errors and that type of thing when you're doing equations, differential equations. Maybe it's partial differential equations too, specifically. I do not recall. So both of these packages, I think, are coming from general equation solvers. And then the model G is the code for specifically the equations we're working with. And since we're changing those equations, then we would be changing that model G code. We may or may not need to make any changes to the other code. Most likely not.
It's just a question of working through this code to try and figuring out what's going on, basically.
Right. And I wouldn't worry too much about this one to start with or the other one to start with. I'd start looking at that model G code because it's what our equations are. The rest, I think, are more solvers. We may be able to use them as is. So, that's my guess.
Okay, that's a good
because
one.
all we're adding is a velocity or a vector of velocity. And I don't know if that's going to change anything from solving
so these
solvers.
Solvers, but what you're saying is if one goes into model G like this,
yes,
and then just alter it here, the solvers will automatically.
Yeah, likely further down is the area that I think you would be modifying. I think the equation is broken up into 2 or 3 pieces, and I'm not sure how it's broken up into 2 or 3 pieces in this code. But you can see solving for G, X, and Y, which are the quantities that we're really looking for there. So there's some type of, I'm not sure what the RV is. I can't imagine it's rotational velocity. So you got the RVG, RVX, so those are the G, X, Y position. That might be the positions. I'm not sure. I have no idea.
It might be, what you're saying, Justin, is by changing these equations, the other solvers will solve it automatically.
Right. Yes. So if you scroll up a little bit, you can see RV is there are 2 or 3 different steps in coming up with the final RV. I know 3 particle, 2 particles. So if you scroll up, there's even some more stuff above it where you're doing some RVs. So there's all this stuff going on with the RV. See all those equations. You do 1, 2, 3, 4, 5 steps. So those might be 4 different parts of those equations that are being set. So we might need to add a 5th step to the equation. So just giving you a flavor just from quick look at all the different pieces of code of what they would be associated with, so it would help us all dive into it. It might take us a few weeks to, I'm guessing everybody has sort of gotten a flavor what this stuff is, and maybe everybody will dive into it a little bit, and then when we come back, we'll maybe see what we can do from an understanding perspective.
So these RVG, RVX is saying this is kind of like,
that's the first part of the equation. Notice it does that. Well, this is an if else. So it does that, or it does the other one, which is a sequence where they make one modification for RVG I, and then later on they make another modification RVGI. Then they make another. Well, that's a comment. The torus is out. Okay, so we can ignore the torus. That's all commented out. But it does the segment first, then it does the 3-dimensional thing, then it does the 2-dimensional thing. And it may be that if you don't want to solve on three dimensions, you comment out that 3D part, and then you're just left with the 2D. If you just want to do, I think 1D, maybe you just use this segment piece. So it looks like he's commenting out different segments of this, because the equation is, this is step 1 of the equation, then later on you go down, step 2 and step 3. Okay, so the 3 particle looks like it's commented out, and the 2 particle is commented out too. So this might be just right.
David is waving. David's trying to say something. What?
Yeah, I
What's
hear you,
David
David.
saying?
He can't hear us.
I can see his mouth moving.
No sound from David.
Okay.
Now I hear you.
What about turning your computer off and restarting your computer? Can't hear. So I had a similar problem. My Wi-Fi wasn't connect. I had to switch my computer on and off two times to get my Wi-Fi working. I tried
Dave,
maybe
David should leave and come back.
Yeah,
and it will fix itself.
Yeah, what I sometimes do is just restart the router, and that often works. But if that doesn't work, just restart the computer, and it often fixes it. Let's just go.
Michael, is he here? I see his name showing.
Okay, so the way he's commented out, it looks like one-dimensional is the first part, and then if you want to run the 2G, you comment the other parts out and you get the 2D. And so it looks like he's just commenting the different sections out in order to run the different pieces of code. And we can clean that code up so that, you just put a variable in and it'll choose which section of code to run.
Maybe David was saying goodbye. I'm not sure. He may have just he may have gone offline and then decided to leave. I'm not sure. I'll write him a note.
What time is it?
What in London? It's in where he is. It's 20 to 11.
So it must be 11:40 where he is, right?
It must be. It's 10:40 where he is.
Oh, what time is it? We still can't hear you.
It's 9:40 where I am.
9:40, okay, and then
David,
10:40.
use your chat to send a message. We can't hear you.
I've sent him a message.
Paul, what time is it where you were in Greece?
Well, it would be 2 hours later, so 11:40.
Okay.
Do you need me? Maybe I'll leave.
No, I think it's
It would be nice if we have somebody report on that something has been done next week. By next week, some in between something to be done, so we have something more to talk about.
Yeah,
if that's possible.
We'll get down to looking at this. Or I'll get down to looking at this ETD stepper and seeing if I can understand enough to make some changes, or at least try and get a better understanding of it and see if I can alter it in some way.
I think that's an error. I think we made some progress today. We said, okay, let's dive into this specific equation that Brendan was working on, and we correlated that with. So this is more of a working meeting, and we correlated with the code, and we talked about the code a little bit. And I think that's, since, if we want progress, we can take it as small steps since not everybody has a lot of time. And we can go over the equations and the code and how they correlate next week. I mean, we can look at everybody can take a look at Runge-Kutta, everybody can look at fast Fourier transform, and everybody can look at the code and see how they correlate.
So I'll put that down. I'll just put that's on there.
It sounds good to you, Paul?
Yeah. Do you communicate with each other in between the meetings? To send emails back and forth about what you're doing?
This is the communication point. This is where we touch base with each other, from my understanding.
It's Facebook mainly. But
and all the Facebook stuff, if you get a chance to look at the Facebook stuff that Brendan's throwing out there, or David's throwing out there, or whoever throws out there. So there's information flowing there.
Well, once we get into it a bit more and start making some progress, then it will be a bit more natural to sort of like
right.
communicate via emails. once, and especially if I get stuck or want to understand something, I could always email Matt Pulver, ask him a question. But once it gets going and we get producing something interesting, then we can communicate via email more.
Okay. If you guys want to continue, go ahead, because it's late here. I'm the
Right.
latest of everyone, so I usually go to bed even earlier than this. But
You have a good evening.
so,
Or night,
okay.
sleep.
Okay,
Good
Paul,
night.
nice to see you again.
Yeah, thanks for all your time. I appreciate it. It's great stuff. Okay. So, did you want to cover anything? My last comment was that code we were looking at, different sections were commented out, and it looks like that's how you run it on 1, 2, or 3 dimensions, just by commenting and uncommenting those sections.
Okay, that's good.
So if you wanted to run, because
my
it looks like
recollection.
it's 1D right now, but then if you wanted to run 2D, you uncomment the 2D. Uncommenting is just taking out the asterisk slash at the beginning and
Okay,
end of a
David, sorry.
section.
Okay.
By
One of the things I wanted to ask you, Justin, is what do you think of my kind of little insight that the one-dimensional plots that Matt Pulver was producing, showing the x-axis as distance and the y-axis as 1, 2, and 3 dimensions. I was seeing that as 1, 2, and 3 dimensions as slices, slice through 1 dimension, slice through 2 dimensions, and slice through 3 dimensions. So the x-axis either is 1-dimensional concentrations, 2-dimensional concentrations, or 3-dimensional concentrations. That was my idea about it.
of what the
We'll work around it. We'll figure it out.
right? Yeah, I didn't really quite understand the question, so I'm just trying to get some details to better understand it. But I think this is a good stopping point. We looked at the code a bit. This one-dimensional thing, I'm really skeptical of doing anything in there if we want any form of rotation, because there's nothing really to put rotation on. 2 dimensions you can put rotation on, because the XY axis and you're going somewhere in between.
Let's just go up to the top. What he's saying here about he says here modeling. Can you see what he's saying here? E++ multiple reactants in 1, 2, and 3 dimensions of space. So that's what I think it is. I think even though he's showing it as a 2. So yes, okay. So this is the ETD stepper. So I'm going to email. What I'm going to do is email Matt Pulver and ask him what does he mean by 1, 2, and 3 dimensional space? How does that?
Okay, so I believe that's in the code we were just looking at. So if you go back to that Model G code.
Model G.
Yeah. And you scroll down and you go to the segment. Scroll down and you'll see segment code right there.
Yeah.
There. Okay, segment. So notice he's got segment work there. So he's defining, okay, and I think we might be able to ignore the DZ. I think it's like the RVGXY. I believe that's the code for 1 dimension. Okay. I'm not sure what the torus is that he might. The first one's the initial conditions, this segment. Okay. I saw your comment. You said that that's the initial conditions. Because you're getting to. Okay, and then you have 3 particles and 2 particles. Okay, that's particles, not dimensions.
maybe that's what he meant by dimensions. He was talking about a dimensional 1 particle, 2 particle, 3 particle. No.
No, it's particles. It's not dimensions. It's definitely particles. Okay, so it's
So that's what he means at the top. That's
because
what he means
if you
by
look,
1, 2, and 3. That's what he means by.
no, it's different.
Okay.
I doubt if he means by 1, 2, and 3 dimensions. Dimensions might be a parameter put in, but I'm not.
Yeah. Okay.
So I was wrong. Those are particles, not dimensions. Because if you look at the equation, each one of them is an equivalent equation. So if you look at it, it's like power V1, C1, and then you've got 2. Okay, so you're going through the each of the different particles, it looks like V1. So you're looking at the speed and not sure how you're doing that. I'm not sure if those are locations that 14, 6, 4, 1, 1, and because these are supposed to be quantities. It is just the initial settings having Gaussian distributions. All of it, 2 particles, 3 particles.
Sorry, Justin, what was that?
He's saying, yeah, see my movies. Okay, he's got some movies there that we need to look at. That these are just the initial conditions, placement where things are, which is a typically an initial condition. You don't toss in that way.
I just want to check that this is
Initial
still
conditions can be
recording.
changed
Let's
using
stop
them as variables at the top.
It's still recording. Okay, that's good. Let's just go back to share. I'll put this up on the Dropbox afterwards. I set it for 5 hours for the meeting, in case you wanted to go further.
Okay. All right. I think maybe one of the things to look at is David's videos first. Where are they stored? David, I'm sure they're in Facebook somewhere, but we got a lot of stuff there and it's not organized. Did you want to share your screen to show the videos, David?
I'll stop my share.
All right, we can somebody look through Facebook, or David can search through Facebook and show us where they are in Facebook. Yeah, Brendan scrolled by a lot of stuff today. All right, I can look myself. What's the term that it's used for under?
Chat. Okay, I see it.
Yeah, just write a comment in the Facebook that just like Brendan's been doing. He put the Runge-Kutta methods and other things in there. Okay, I see physics stack exchange. No, it's a different one. Video.
I've made a copy of this. on
Is it the March 3rd comment at 3:45? Okay, February 17th. Okay. Okay, that's February. Okay.
Can you see that, Justin?
I'm seeing. I found it myself. The February 17th link. Yeah. Okay. 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 So scroll up. If those are just initial conditions, where are the equations?
Who are you talking to, Justin? Are you talking to me or David?
Either one. Scroll up, see where the equations might be.
Can you see that? Can you see my share at the moment?
Yeah, just scroll up. Yeah, so you're really not seeing any equations, right? All right. So it might be in some other piece of code.
Okay, he wants us to look at the yeah, difference with the
Seems to work. Hello.
hello.
Can you hear me now?
I can hear you. But I can't. You're static now, so I can't hear you. Okay, I'm gonna copy